Howdy and welcome to the next lesson, which is on vector equation of a line, which I think was kind of missing from the top of your notes. I should say L for vector equation of a line, so feel free to add in the N and the E on the end. Okay, so let's warm up again. We'll do two little quick warm-ups. So find the angle between the vectors v equals 3i plus 4j minus k and w equals negative I plus 2j plus k. So these are 3D vectors in ijk form as opposed to column vectors. Feel free to rewrite them as column vectors. And remember, in a previous lesson you learnt a formula for finding the angle. So yeah, and so on. So from the exam formula booklet. So this one is actually the rearranged version, but if you forget what it was, what the actual equation was, you can kind of look back on a previous one. So remember, it is that the, so this is the dot product or the scalar product. So the scalar product is equal to the magnitude of v times the magnitude of w cos theta. So basically, if you kind of multiplied these two things over here, you would have, and rewrote this as v dot w, like the dot product, then you would have the original formula that's in the booklet. So this is the rearranged formula from the exam formula booklet. They don't give you the rearranged version. So you need to be able to rearrange it yourself, but that's easy enough. So remember, to find the dot product, you could write it as a column vector, if it helps. So if you wrote it as a column vector, you'd have v as 3, 4, negative 1, and you would have w as negative 1, 2, and 1. And then you do that times that, plus that times that, plus that times that. Is basically what you do. So if you kind of ended up with that, you'd end up with 3 times negative 1 plus 4 times 2 plus negative 1 times 1 is the dot product. And you would work that out, and then you end up with negative 3 plus 8 plus negative 1 and work out what that is. And then under here you've got the magnitude of v and the magnitude of w. So remember, to find out the magnitudes, you use for a 3D vector, you use a Pythagoras in 3D formula. So the square root of 3 squared plus 4 squared plus negative 1 squared for this, for v. And for the magnitude of vector w, it's negative 1 squared plus 2 squared plus 1 squared and the square root of that. Then try to combine these, you get root 26, and this one becomes root 6. So remember, root 26 times root 6 is the square root of 26 times 6. So just be aware of that, and try to think what's negative 3 plus 8. Right, it's 5, and then 5 plus negative 1 would give you 4. So 26 times 6 is 156. So if you do square root of 26 times square root of 6, you'd get square root of 156. So 156 is divisible by 4. The way you can, and so you can simplify the third. It's actually also divisible by 16, it turns out. So you could, it's divisible by 4 because the last two digits are a multiple of 4. And so what you could do is you could kind of simplify it by taking 2 out the front. So then you'd have 2 root 78, and then 78 is also a multiple of 4. So then you would have to take that out as well. So that, or alternatively, if you realize it's 16 goes into 156, you can go straight into taking 4 out and dividing this by 16. And then you would get that. And then 4 over 4 simplifies to, so 4 over 4 simplifies to 1. So you'd get 1 over root 39 for that particular answer. And remember, this is just what cos theta is. So cos theta equals 1 over root 39. So therefore theta is cos minus 1 of 1 over root 39. Pop that in a calculator, because this would be a calculator question in this case if you're expected to work out this. And you would get 80.8 degrees. Okay, another warm-up. Given that the two vectors v equals I plus 2t plus minus ij minus 3k and w equals this is looking like a scalar product and perpendicular kind of question. So if those two vectors are perpendicular, meaning they meet at right angles, find the possible values of the constant t. So this is one, remember, when two vectors are perpendicular, what does that tell us about their dot product or their scalar product? That's right, if they're perpendicular, their scalar product equals 0. So what you can do is set up an equation for their scalar product, set it equal to 0, and you can solve it. So again, if it helps to rewrite these as column vectors, you can. You would write it as 1, 2t minus I, and negative 3. This one you would write as 3, And then if you want, you could expand this. So you could do -2 plus t. So -2 plus t if you want. And then 1. And then you would do that times that plus that times that plus that times that. If the perpendicular scalar product equals 0, that is. So you would do 1 times 3 to work out the dot product plus this times this, because notice that if you factor in negative here, you get -2 plus t. A nicer way of writing -2 plus t is t minus 2. So in here, we've already kind of factored in the negative, because it should be, basically, what overall is this? And overall, this is net minus 2 plus t. So we've done that one times that one, and then multiply the -3 by 1 here. Set it equal to 0, and then you start to multiply this. You would FOIL this, combine like terms, and multiply this, and then combine like terms again. So upon doing that, you would get 3 here. Here you'd get 2t squared, then you'd get -4t minus 1t, and then -2 times -1 times -2 is plus 2, and then this is -3. Then you would combine like terms, so you could combine the minus 4t and minus t. What's that? You can also combine 3 plus 2 minus 3 and see what that is. And hopefully you would get this, because you've got 2t squared minus 5t. 3 plus 2 is 5. 5 minus 3 is 2. And then now factorize this. Factorize by hand is probably a good thing to do. Practice your factorizing by hand. Again, it's really easy to just pop it into Polysmall, and I can remind you of how to do that again later. But let's try it by hand. So this one, first of all, look, is there a common factor that you can take out? No, there's not a common factor, so we'll have to factorize this quadratic using the splitting method, because we've got a value greater than 1 here. So remember to do the splitting method. You go, what's 2 times 2? It's 4. Then try to think, what's 2 numbers that multiply to give 4 and add to give -5? So 2 times 2 is 4. So basically you end up with -4 and -1, because -4 times -1 multiplies to give 4, and -4 plus -1 gives you the 5. So basically you've got to split the minus 5t into -4t plus 1t, plus -1t. So 2t squared, so this, we split this middle term here into minus 4t minus t plus 2, because see, minus 4t minus t is still minus 5t. So overall, this is the same equation. And then you separately factorize this bit, separately factorize this bit. So what's the common factor here? The highest common factor is 2t. And here, what's the highest common factor? It's probably -1. So take out 2t here. If you take out 2t from this bit, you're left with t minus 2. Take out -1 here, because these two brackets have to have the same thing. So if you took out +1, you would end up with minus t plus 2 here. We need to end up with t minus 2, not 2 minus t. So to do that, you need to take out -1. So -1 times that gives you that. -1 times that gives you that. And then, so one of the brackets is t minus 2, the other, and these two things make up the other bracket. So see, t minus 2 is one of the brackets, and these two things make up, the remainders make up the other bracket. And then separately solve them. If t minus 2 equals 0, t must equal 2. If 2t minus 1 equals 0, 2t equals 1, and then t equals 1 over 2. That's how you get those two values. I'll remind you again how to use Polysmall. If it was calculator, so if it was with calculator, you would just from here go put it straight into Polysmall. So you would go apps, Polysmall. Make sure you've always got a calculator and you're practicing doing this. For us, it's harder to remember in the exam if you've only just watched. So degree of polynomial is 2 because it's a quadratic as opposed to a cubic or a quartic. So let's go on to the next. So we've got 2. It's a square term. The t term is, what was it, -5. Could use the negative button. And the constant term is 2. And solve. Let's see, we get t equals 2, t equals 1/2. Okay, now let's move on to the actual thing that we're doing now, which is this. Okay, vector equation of a line. Okay, so let P and Q be vectors. So let those be the position vectors. Remember, position vectors originate from the origin. So they start at the origin by definition. Position vectors of points P and Q with respect to the origin O, of course. Let R be the position vector of point R on the line PQ. So this vector connects OP, this vector connects OR, this vector connects OQ, points O and Q. So therefore it pointed out that OR, so OR is the same as doing OP plus PR. It's pretty obvious. OR is the same thing as OP plus PR, which equals OP plus T of PQ. So T is what fraction is this compared with the entire thing? Like, is this a third of PQ? So is T a third? If this was a half, like if R was in the middle, then T would be a half. If this was a quarter of the way across from PQ, then T would be a quarter. So because PR is just a fraction of what PQ is. Like T is a scalar, like a third, a quarter, a half, a fifth, whatever it is. 2/3. So therefore, R equals, if you write it in terms of the bold lowercase vectors, R equals P plus T of Q minus P, because Q minus P is PQ. See PQ here is the same thing as negative P plus Q. So PQ is the same thing as negative P plus Q, which is a nicer way of writing it is Q minus P. So notice OP is P, so they're just replaced. OR is R. So they replaced OR with R, they replaced OP with P, T is still here, and PQ is the same thing as Q minus P. Q minus P. And so on. And alternatively, if you expanded this in, you get R equals P plus TQ minus TP. Or R equals P plus TD, where D equals Q minus P. So D is another thing that's kind of just been imagined up. So D could be Q minus P. This is the vector equation of the line PQ. The vector Q minus P is what we call the direction vector of the line. So this is kind of getting a little bit abstract now. So D is for direction vector. So notice what you've got here. So you've got P going on here, and this D here. So we've got P. R equals the vector equation of a line, R. So if you want the vector equation of the line, it's P plus a scalar multiplied by D, and D is the direction vector of the line. So it is getting a bit abstract now. So Q minus P is the direction vector. So we've got P plus T, Q minus P, but this part here you could call D because Q minus P is the direction vector, which is this one here because it goes in this direction. So those two circle points are important to remember. Basically, the vector equation of a line here, and that Q minus P is the direction vector of the line. They're both important points to remember. That's why they've been circled. Other things to remember. Each value of the parameter t, so remember t is this little thing here, like what fraction of the entire line is this little bit here, basically. So each value of the parameter t corresponds to a point on the line, PQ. So what on earth do we mean by that? So when t is less than 0, point R is on the line QP produced. So see here, when t is less than 0, point R is on the line that QP produced. What do we mean by QP? We mean QP here. So if you're having trouble seeing it on there. So on mine, I'm kind of missing QP. So there should be a Q and a P there. Okay, so when t is less than 0, like out of here, so basically if it was negative a third, then it's over here somewhere basically. Point R is on the line that QP produced. It's not on the line QP, but it's on the line that QP produced. When t is equal to 0, it would be right here. So it'd be right there. So point P is here, point Q is there. So if t is 0, then the point is right here, as in point R would be right there. So when t is 0, therefore vector R would equal P, because we're talking about this line OR. So if t is 0, then it's over here somewhere. Oh, sorry, it's just here. If t is less than 0, it's over here somewhere. And that is, so therefore, if it was t is 0, then these two lines would actually be the exact same line, vector. So it'd be going along here. That is r equals p, because r would be sitting on top of point P right there. Here's point Q, here's point P. If t equals 0, that means r is right here. And the vector's not there, it's here. Now this is confusing, so that's why I keep going on and repeating myself. So what about when t is between 0 and 1? So between 0 and 1 means anywhere between here. Then point r is between p and q, which makes sense. So this would be an example of when t is between 0 and 1, because point r is between p and q. Here's q, here's p. When t equals 1, it's right over here. So when t equals 1, then point r would be sitting right on top of point q, and therefore vector q would be the exact same thing as vector r. So that's why they're saying r equals q for that one. And when t equals 0, r equals p. And another one, what about when t is greater than 1? So when t is greater than 1, that means the vector r would be kind of like popping out this way instead. So when t is greater than 1, point r is on the line that pq produced. So basically, because here's p going to q, so basically by produced I mean if you extended. If you had the line pq, so if you were drawing the line pq and you extended it, then in this case point r would be sitting out there somewhere on that line that was produced by extending. Basically by this I mean on the line pq produced by extending itself. And therefore when it was this way, so when t is less than 0, then this would be on the line that qp produced, because starting at q, going to p, and extending itself. If this makes any sense at all, fair enough if you're a bit confused. So as I said, overall, each value of the parameter t corresponds to a point on the line pq, basically. I was trying to point that out. So let's try to see this in action. So see, how do we apply this? So find the vector equation of the line passing through point P, 1, 3, 2. So P's got the coordinates 1, 3, 2, and 3D coordinates obviously, x, y, z. And Q, 0, negative 1, 4. So these are position vectors because they originate from the origin. So therefore, if they're position vectors, their coordinates tell you what the vector is. So the column vector would be 1, 3, 2 for this one. And the x, y, z coordinates of this one similarly tell you what the vector OP would be. It'd be 0, negative 1, 4. Does the point R, negative 2, 9, 1, lie on the line PQ? So does it lie on the line PQ, or is it out here somewhere, or is it out here somewhere? So to decide if it lies on the line, we've kind of got to follow these rules. If it lies on the line, then T is between 0 and 1. So it'd be in here somewhere. Okay, so the position vectors of P and Q, as I said, would be 1, 3, 2, because they originate from the origin, so therefore you can just use their coordinate to write their vector, because they come from the origin. So basically that minus, so the origin is 0, 0, 0, and then you've got 1, 3, 2. And so basically the 1, 3, 2 minus 0, 0, 0 would produce this vector. Same with this one. So write the P and Q as position vectors is the way you would start. What would you do next? So remember that from the previous slide, the vector equation of a line is given by, actually it wasn't the previous slide, it was the one before, R equals P plus T, Q minus P. Remember, this is the direction vector. Just going back to if you forgot where that came from here. This is the direction vector. So that's why I said these circle things are really important. R equals P plus T. T is just a scalar. Q minus P is the direction vector. So back to here. So the vector equation of the line is given by R equals P plus T, Q minus P. So we know P and we know Q. So that kind of makes life a bit easier. So therefore, notice we can replace P with whatever P is, 1, 3, 2, plus T. And in here we've got Q minus P. Q minus P is what goes in here. So what we're doing is we're just subbing it into the vector equation of a line. So now you can work out, basically, you can work out what Q minus P is, what's 0 minus 1, negative 1 minus 3, 4 minus 2, and you can simplify this a little bit here. Oops. And then you would get, so you've got r equals 1, 3, 2, and then this simplifies to -1, -4, 2 when you work out this bit, and you've still got the t there. So we've worked out the vector equation of the line. So we've got our direction vector here, which is important. So alternatively, this could be, this is in kind of column vector form for the vector equation of a line, just pointing out that you can also rewrite this in ijk form. That's possible too. So how would you do that? See, r equals ijk. So notice, how did we kind of get this? So basically, you're kind of like expanding this bit. Because it's kind of like, if you kind of like times a t in here, you've got 1 plus -1t, which is 1 minus t. Here you've got 3 plus -4t, which is 3 minus 4t. Here for the j, and for the k, you've got 2 plus 2t. So seeing that you can kind of just expand this and kind of combine them all and put them into ijk form. So you can have them as column vector form, you can have it in ijk form as well. Let's do some more of this. So it continued from the previous slide, because what were we asked? Oh yeah, so we've found the vector equation. Now, so we've done that, that's fabulous. Now up to this point, don't forget there's a second part to the question. Does the point R, -2, 9, 1, lie on the line PQ? That's something we've got to work out now. So that's what we're doing now. If the point R, -2, 9, 1, lies on the line PQ, there will be a unique value of t, for which basically these all equal that. So basically, if you're able to get a value of t that kind of satisfies this, then you're good. So what could you do? Try to think. So if -2 equals the first part 1 minus t, you can see where we're getting that from. We're getting that from these three things. So these three things is what we're kind of setting up. So that's where those three things came from. And we're setting these equal to those three things. So if -2, as we said, equals 1 minus t, then in that case, if you solved for t would equal, you'd pop t over here and you'd add 2 here, and you get t equals 3. However, does t equals 3 satisfy this? So that was meant to be hiding there. So if t equals 3, if you sub 3 in here, 3 minus 4 times 3 is 3 minus 12. Would you get 9? No, you wouldn't. You would get -9. So if this point R lay on this line, then that value of t would be the same for all of them. Whereas if you solve for t here, you get -9. Well, basically, no. So if you solve for t here, you'd get a different value. So basically, if you did 9 equals 3 minus 4t, then you would get a fraction. You'd get something like 2/3 or something like that, or 3 over 2. And same thing if you did 2 plus 2t. So basically, I just solved one of them. Solve the one that's the easiest one to solve. This was the easiest one to solve. And then the quick thing to do is to sub it in and see, does that equal that? If you sub in 3, does that equal that? If it does not, if you have different values of t when you solve them, therefore, you can just say this, you can conclude that the point R does not lie on the line. If this point R did lie on the line, then whatever value of t you got from solving the first one would also be the value of t for the other ones. Or if you sub in t, you'll get that. If you sub in t is 3, you'd get that. So that's a quick way to work it out. So there's a lot in this kind of lesson. So it's a little bit confusing and a bit abstract. So feel free to play stuff back again and watch it again. We'll do some more examples too. So note the value of t must satisfy all 3 equations. It can't just be 2 of them. So you can't just check with 2. You've got to check that it satisfies all 3 of them for the point R to lie on the line PQ. Here's another example. I'm going to do a couple of them now. So 2 lines, L and M, have the following vector equations. So we've got a vector equation worked out here and a vector equation worked out here, respectively. Find the position vector of their common point. So position vector meaning what would it be from the origin. And find the angle between the lines. That'll be easy enough. Okay, so let's do that. So rewriting the vector equations of the two lines in column vector forms just makes life a little bit easier. So this would go here, this, the J, and then the K is 4S. Don't forget the S there, that could be easily missed. And then this one would be here, that would be 3, and that would be 7 minus T. So writing them in column vector form makes it a little bit easier to start with. At the point common to L and M, R of L equals R of M. That's an important point. So if they have, we're trying to find the point position vector of their common point. So we're trying to solve to work out what is the position vector of their common point. Whatever point they have in common, these must be equal to each other. So set these equal to each other basically. So let's set them equal to each other. And what could we do then? So if you set them equal to each other, you could do a fair bit of solving at this point. Because basically that should equal that, that should equal that, and that should equal that. Let's continue this on the next slide. So equating the I and j coefficients, like I just said, that one equals that, that one equals that, that one equals that. So we've got three different equations going on here. So we could do all sorts of things, like according to this one, you can easily work out that S must equal 3 minus 1, S equals 2. That's easy enough. So from equation 2, you can solve that one, and you've got S equals 2. And then what you could do to solve for T, you could sub S into this one. Might be a bit easier if you sub it into this one. This is an easy one to sub in S equals 2. Sub in S equals 2, you get 8 here. So if 8 equals 7 minus T, so therefore T must be negative 1, because 7 minus negative 1 equals 8. So that's what this was just trying to point out, that you can solve. You might want to double check by subbing in S is 2, T is negative 1, and double check with this equation as well. Notice that S equals 2, T equals negative 1 also satisfies equation 3. So they did equation 2 to solve for T, I did equation 3, but then I would double check my S and T values by subbing it into equation 1 to see, does the left-hand side equal the right-hand side? So at the common point, therefore, you would just sub in. So at the common point, you could use RL to sub it in. 2 minus, basically what we're doing is, we're subbing in S and we're subbing in T for the common point. So at the common point, 2 minus 3, sorry, where's that coming from? Coming from here. So I'm using this one here. So basically, I've subbed in 2 into here, subbed in 2 here, and 2 here, and that's easy enough. You could always sub in T to the other one, sub in T to this one. What do I mean by that? Sub in the T value into this one to double check your answer. So if you sub in 2 into RL, then you end up with negative 4, 3, and 8. So that's the common point. And was that what I was asking for? It said find the position vector of the common point. Now we've got to find the angle between the two lines. So the position vector of the common point is negative 4i plus 3i plus 8k. 3j. Oh, whoops, that's meant to be a j, by the way. So change this one. So go back, and if you wrote negative 4i plus 3i plus 8k, that's a mistake. Please change this one to a j. Must have just gotten cut off. That should be a j there. So I've just repeated the question. Now we just need to answer part B of this question. So we've already found the position vector of A, which we've got here. So you might need to use that, you never know. So we will need to find the angle between the two lines. So we know that R of L is this one, as a column vector form. We know that S equals 2, so, and so on, equals, hang on, 2, where did we get that from? Just one second. Oh yes, I see, we're just breaking it up into the vector equation. Because remember, you've got, like, the vector equation of a line is like P plus TD, and that's Q minus P. So basically they've broken it up. So here you'd have 2, 1, 0, and because S is the scalar, that's as if it was the T, like the little value of T. So S is the scalar, and then the coefficient of S is negative 3, coefficient of S here is 1, coefficient of S here is 4. So that would be 2 minus 3s, 1 plus s, 0 plus 4s. So basically it's broken up into the vector equation of a line form. So here's our direction vector here. And on top of that, we also know that r of m was this one, same thing. The scalar in this case would be t. So we've got -1 plus 3t, which we can write -1 plus 3t. Here's our direction vector. We've got 3 plus 0t. You would write that because there's no t next to that one. 7 minus t, 7 plus -1t. So we've kind of got those two vector equations of the lines worked out now. Therefore, the direction vector of the line, L, is -3i plus j plus 4k. So here's the direction vector here, because we've got to use the direction vector in order to find the angle between the two. So this is the direction vector, remember, by definition. This is the direction vector of this one by definition. So therefore, the direction vector of the line L is this one, which came from here, -3, 1, 4. And the direction vector of line M is this one here. So that's why I've got 3 minus k, because it's 0j. It's fine if you're at 3i plus 0j minus k. The angle between the lines L and M is the angle between these two direction vectors. Because it doesn't matter about the magnitude, it's the direction that determines the angle, the direction of the vector. So we use a direction vector to work out the angle between the two. So just pointing out where that came from there, and that one came from there. So look back at the bottom of slide 4 to recall what a direction vector was. That's just what I was pointing out, like, you know, the vector equation of a line. Just reminding you as well, in your formula booklet, it's here, vector equation of a line. So they don't write P plus TD, they write A plus TB. But B is a direction vector. That's the main thing to remember. V is a direction vector, T is just a scalar. So back to here. Next slide. So now we've got to find the angle between them. So remember in the formula booklet, as I pointed out, hang on, do they give you the rearranged version? No, they don't. Oh, yes, they do. Actually, they do give you the rearranged version. So I forgot that. They give you the rearranged version. So the angle is, they basically rearrange this one for you, which is so easy to do anyway. The dot product divided by the magnitude of V, magnitude of W, cos theta, and you'd cos minus 1 that. And dot product is that times that, plus that times that, plus that times that. Back to here. So using that, so I've just gone straight to subbing that in. And then because our previous, there are two direction vectors, so here's the other one. So basically to get the dot product, you do that times that, plus that times that, plus that times that is what we're doing on the next one. And so on. So that's where we're getting these ones from. So just replacing the letters L and M with U and V so we can use the formula above. So because it was line L and line M, don't have to change it into U and V, that's fine, just go straight to subbing it in. So work out the dot product and also work out the magnitude. So I've got to work out the magnitude of the vector. So square root of each of these squared, -3, 1 squared, 4 squared, square root of 3 squared plus -1 squared. You could also include plus 0 squared in there. So you get root 26 times root 10, times them together, you would get square root of 260. The dot product, as I said, would be that times that plus j times 0, I mean 1 times 0 plus 4 times -1, which when you work this out, you get -13. So at the moment, we've kind of ended up with cos theta equals -13 over square root of 260. So theta equals, and because notice it's negative, so the negatives there, don't miss that by mistake when you're writing out your working out. So to solve for this, we need to do cos minus 1. So we do cos minus 1, -13 over root 260, and you would get 143.7 degrees. Feel free to try it in your calculator if you're not sure how to do it. Just reminding you things to do on your calculator. How to do it on the calculator in case for some reason you forget. So you need to go to mode, make sure you're in degrees, because like you might have switched between radians, and my calculator's seizing up what's going on. Okay, great. Mode. So see, yep, I'm in degrees, that's what you want to check first. Get back to the calculator screen. Second cos, to activate cos minus 1. If you could put in -13 over root 260, you could also, if you prefer, go alpha y equals and make a nice fraction if you prefer that. Pop a negative at the front, negative at the top, doesn't matter. -13, So negative 13 could have been the numerator instead, over root 260. Voila. That's how you get. So remember, write your unrounded answer first, and then write the rounded answer. Here they've gone to one decimal place. So the angle between the lines, L and M, is 143.7 degrees in that case. Okay. So here's another example. I don't know what that was about. Sorry, this question. Here's another example. Find a vector equation for the line passing through the point 35 and parallel to vector 2i plus 3j. So because it's parallel, that might help us to work out what the direction vector is. Remember that the vector equation of a line is this thing here. Feel free to write what's in the formula booklet too, because remember in the formula booklet they've got r equals a plus tb, where b is the direction vector. So p plus t, q minus p, whereby p is a point on the line, t is just a scalar multiple, q minus p is the direction vector. So same thing with this one. A is a point on the line, t is a scalar, b is the direction vector. Feel free to write that because that's what's in the formula booklet. We've been given a point on the line and the fact that the vector is parallel to 2i plus 3j. This tells us the direction vector. So the fact that the vector is parallel to this one means that we've got the direction vector already, and we've got a point on the line. That's fab. So how do we pop that into the equation? The point, so that's a coordinate. So this needs to be the position vector of that coordinate. That's a point on the line. Its position vector, therefore, from the origin would be 3, 5. And plus t, because that's our scalar, and our direction vector, because it's parallel to, the vector's parallel to this one, so it must have the same direction, so 2, negative 3. So that's our vector equation of the line. That's a nice simple one. And another similar example, because this is a little bit hard to get your head around. So find a vector equation for the line passing through the point 3, negative 2, and perpendicular to vector I plus j. So it was easy when it was parallel, but now it's perpendicular. So what do we have to do then? So we already have a point given to us, which is 3 minus 2, so that's easy enough. So its position vector would just be, so A, or whichever thing you call it, if you're looking at the formula booklet, then A would be basically the position vector of that point. So we would have 3, negative 2. We just need to work out the direction vector based on the fact that it's perpendicular to vector I plus j. So remember, as our line is perpendicular to vector ij, their scalar product must equal 0, because if two lines are perpendicular, like at 90 degrees, their dot product or scalar product equals 0. So it's a very helpful thing to remember, the fact that when two lines are perpendicular, their dot product equals 0. Therefore, our direction vector could be something like I minus j, because this would lead to a scalar product of 0. Because if you worked out a scalar product of this, like, then you'd get that plus that, that you'd have 1 times 1 plus negative 1 times 1, which equals 1 minus 1, which is 0. So we basically need to come up with a vector where if you found the scalar product of these two, you'd get 0. So it'd be a little bit of kind of trial and error problem solving using logic kind of thing, because you'd have to think like that times that plus that times that, or any kind of multiple really, because if you had 3i minus 3j kind of thing, you get 3 times 1 and times negative 3 times 1, and so that would also work. But I minus j is nice and simple then compared with something like 3i minus 3j. So the answer is this one. Remember that you've got your a plus t b according to the formula booklet instead. So your point on the line, its position vector would be 3 minus 2, because position vector is its vector from the origin. And then plus t is the scalar, so we just leave it in there. And 1 minus 1, because if you have 1, 1 and 1 minus 1, their dot product would equal 0. So you know this one's perpendicular to that one. So that's the vector equation of the line. Just things to keep an eye for, like just reminding what is a perpendicular bisector, because sometimes you might find an exam question where they kind of assume you remember what a perpendicular bisector is. So I thought I'd just point out what a perpendicular bisector is again. Perpendicular bisector, it's a line which cuts through the midpoint at 90 degrees. So if you've got, for example, a line here, this perpendicular bisector would cut through it, cut through the middle of that original line and at a right angle. So if this was the original line, its perpendicular bisector would slice it in half, and it would at 90 degrees. So just reminding you what a perpendicular bisector is, in case you've forgotten from GCSE or earlier years. So a perpendicular bisector is a line which cuts through the midpoint at 90 degrees. Therefore, find the midpoint of the two coordinates first, and then find the vector which joins the 2 points to find a direction vector for its perpendicular. A bit complicated. So you might not see a question like that, but I just thought I'd point out what a perpendicular bisector was. And just reminding you, in the formula booklet too, they have coordinates for the midpoint of a segment. And so in the formula booklet, they have coordinates for the midpoint of a 3D. So if it was a 3D kind of segment, or if it was a 2D segment, you would just use these two. Hope this hasn't been too overwhelming. This was a pretty intense lesson, so fair enough if you're a little bit confused. I'd just suggest do lots and lots of practice questions from the textbook. Thank you.